all of us closely working on the multimodal LLMs and the relevant topics. So first, let me give a brief introduction to this grand topic of MLLM. My name is Hao, a research fellow at NUS. And yeah, let's start from the magic scaling law. So in the field of AI, over the past 2 decades, researchers have discovered that when dramatically increasing model parameters and data, remarkable phenomena occur. Larger models lead directly to the emergent behavior, right? So as we have seen, under the scaling law, we have fully entered the era of LLM in the last 2 years. So with the emergence of LLMs, today's most advanced purely language-based LLM, like ChatGPT, have nearly approached the human-level intelligence. For example, current LLMs have an unprecedented capability for very deep semantic understanding of language. Here I just showcase an example. And incredible numeric analysis capability, also the amazing mathematic reasoning ability. And there is a crazy trend in the research community about LLMs just last 1 year. So our research on LLM is progressing rapidly, and new iterations of various LLMs are emerging at a very fast speed. So now let's go back from the language-oriented LLMs to the multimodality. We all understand that the language is only one part of the sensory world we live in. We consistently perceive the information through various modalities like vision, sound, 3D, depth, taste and smell, etc., not just language only. So in practice, there are many applications requiring multimodal data, such as autonomous driving, medical diagnosis systems, and smart home assistants. So this prompts the research community to think one important question: can we transfer the success of LLMs to MLLMs? So enabling to comprehend multimodal information as deeply as they understand the language. So achieving true AGI will undoubtedly require the ability to perceive and interact with the world through various modalities, pretty much like we humans do. Fortunately, the MLLM community has gained significant traction over the past 1 or 2 years, and is now developing so rapidly. Yeah, you just feel it from this roadmap. A lot of MLMs are invented every month. Yeah, another roadmap. So this tutorial is dedicated to giving a thorough tour to MLM topic. So in what follows, I try to answer. First, what we have achieved about MLMs, we will walk through the, I think, 4 key technique aspects around MLMs and give detailed taxonomy of existing research. And 2, where to go next of each aspect. So we provide insights and describe the open challenges and then spark future directions. So we believe these are the 4 key aspects for building more powerful and capable MLMs. So okay, we may take 1 more minute for the technique issue. Oh, I see. Okay. So I'm actually muted a couple of minutes. Okay. Sorry for the online guys. I just muted. Okay. So we believe there are 4 key aspects for building more powerful and capable MLMs. First of all, the architecture and the modality of MLMs. And second, the multimodal instruction tuning. Third, human level modality reasoning. And the last of all, efficiency construction of MLMs. All of these four parts together can lead, we believe, to the goal of building stronger MLMs towards human-level AI. So for the first part, MLM architecture design, me and Yuan Yao, he will be online. We'll together give the tutorial. So we answer, what is the current architecture of MLMs? What modalities and the functionalities do MLMs support? What will the next generation of MLMs look like? This part will take like 19 minutes. Fuxiao Liu will introduce multimodal instruction tuning. So multimodal instruction is one of the key parts of the right now, the MLM. So he will answer why, what, and how is multimodal instruction tuning? What is the challenge? So this part will take like 40 minutes. Next, Zhuosheng Zhang will elaborate on the multimodal reasoning of in MLMs, bringing the latest developments in multimodal reasoning. This part will take like 40 minutes. Lastly, finally, Ao Zhang will introduce MLM efficiency problem, like what is the most efficient MLM architecture to achieve high performance. This part will take like 30 minutes. The overall tutorial will start from 2 p.m., but actually we just waste like 20 minutes, but so it will span 4 hours. So in the middle of the tutorial, we'll have 30 minutes for the coffee break. For more materials, please visit the tutorial homepage, and also you can raise questions after each sub-tutorial or join the Google group for discussions. So we will go on. Continue the next part. So, but also I understand that here COLING is an NLP conference. So I'm quite curious about how many of you are working on MLM or just MLM related topics. Would you please let me know the fact? Please raise your hand if you are working on the MLM and okay, good. So many of you still stick to the NLP. Actually these 2 years, so many standard regular NLP tasks are actually impacted by the emergence of MLM. Like so many of them are just quickly nearly solved by the LMs. So actually some of NLP researchers have to consider extending the research scope from the pure text to the multimodal information. So thank you for still sticking to the NLP research and the flourish NLP community. Okay, I need to change it to the first part, another slides. Good. Without further ado, let's go for the first part. MLM design, architecture, and the modality. So this part, me and Yuan Yao will be the presenters. Okay, let's quickly go through the content. For architecture, I'll summarize how the MLM is constructed, including the encoder, tokenization, projection, backbone LMs, and the decoder. Then I'll showcase what modalities and the functionalities existing MLMs support case by case. Finally, I'll slightly introduce some benchmarks for MLMs evaluations and soon introduce the interesting thing, the levels of MLMs, and finally we'll give some insights to the future trends of these MLMs. So section 1, architecture of MLMs, how to design an MLM. Before constructing MLMs, we all reach a consensus and acknowledge a key premise that, as I mentioned earlier in the introduction, so due to the scaling laws and the emergent phenomena, current language-based LMs already have powerful semantic understanding capabilities. So this means that the language has already been a key modality for carrying the intelligence. So given this premise, language intelligence has been considered as the pivot for multimodal intelligence. So nearly all MLMs are built on top of language-based LLMs. Please, yeah, please. Of course. Okay. So right now everything is works smoothly. Okay, good, good, good. I don't know how many things just missed. Okay, finally. Okay, we just take a few minutes to fix some technical problem. Okay, how about we start all over? Yeah, just from the section one. And I will introduce how to design an MLM. especially for a beginner. So before constructing MLMs, as we all reach a consensus, like just as said, due to the scaling laws and the emergent phenomena, so current language-based MLMs already have powerful semantic understanding capability. So this means that the language has already been a key modality for carrying the intelligence. So given this premise, language intelligence has been considered as the pivot for the multimodal intelligence. So nearly actually all the existing MLMs are built on top of language-based LLMs as the core decision-making module. It's like the brain or central process for the decision-making. In other words, by adding the additional external non-textual modality modules, I mean the encoders or decoders, LLMs are enabled with the multimodal perceptual option abilities. So based on this premise above, two MLM architectures actually have emerged. So the first step is the LLM as a discrete scheduler or say controller architecture. As shown in the illustration here, the role of LLM is to receive textual signals and instruct the textual comments to call the downstream modules. All messages passing within the system, such as the multimodal encoder to the LLM or LLM to downstream modules actually is facilitated through the pure textual comments as the media. Representative MLMs of this type includes the visual chat GPT, Hugging GPT, etc. Let's take a closer look. So in this architecture, LLM like a ChatGPT are mainly used as the central scheduler, or you can say the task dispatcher, and let LLM delegate the user's input queries to various external functional modules which execute the relevant tasks. Yeah. So the second architecture that has emerged over time is called the encoder LLM decoder framework. This is actually the most popular architecture. So the role of this LLM is to perceive multimodal information and react by itself in a very in a structure of encoder LLM decoder. So the key difference between this one and the above one is LLM as the key joint part of the system receives multimodal information directly from outside and delegating the instruction to decoders or generators in a more smoother, more smooth manner. So in such framework, I mean the encoder and decoder framework. So as illustrated here, the encoder handles encoding, signals from multiple modalities. The LLM serves as the core decision maker, and the decoder manages multimodal output. Please note that since the backbone LLM natively supports text input and output, so no additional encoder is required for the text processing. Yeah, benefiting from joint learning, which will be elaborated upon shortly. So this paradigm is more promising. Actually like 96% of the MLMs adopting this kind of architecture. So this section will later focus on this type of architecture with the detailed instruction. Specifically, it will cover several key components like the multimodal encoders, multimodal connectors, multimodal tokenizations, the LLM, and the multimodal generators. Yeah, as I said, is very promising. By the way, the figure credit to this awesome survey. Let's start with the multimodal encoders, which functions to encode various not text modalities and generate corresponding modality feature representations. So first up is the visual encoder. Yeah, let's begin from the visual encoder, because we say multimodal is go beyond not only the vision, right? So let's first up is a visual encoder, including both the image and the video. So currently, Clip VLT is the most popular choice for vision language models. It offers two key benefits. First, providing the image representation that are well aligned with the text space, and the second, scaling efficiently in terms of the parameters and the data. But the Clip VLT also has certain limitations. For example, it may fall short in handling some only support the fixed resolution, which may be low in some certain scenarios. For example, so this will lead to some information loss actually. But you know, in many of scenarios, high resolution perception is actually very crucial. For example, for the OCR capability, right? So as a result, recent research has focused on the approach to improve the resolution issues. For example, the image slice-based methods and the draw branch encoders and the VIT-free approaches. Okay, for other non-textual encoders, most models typically rely on the most established modality-specific encoders developed before the LLM era. For example, for the audio, Herbert's, Whisper, and the Beats are most commonly used. For 3D point clouds, the point BERT is a popular choice. Besides using separate encoders for the different modalities, another emerging trend is the adaptation of the unified multimodal encoders. So this type of approach offers a unique advantage for understanding multiple modalities, particularly when the MLLMs are designed to cover a wide range of modality types. So the key idea is to align all modality features into a shared representation space through pre-training using a unified encoder. So the first notable model is this one, ImageBand from Meta AI, which embeds 5 important modalities into a joint representation space, which are centered around the images. So another model is called the language band, which, as the name suggests, align different modalities into a language pivot space. So why language? Because as I said, the language, actually have seen the intelligence, right, with the LLM. So this approach leverages language as the central modality to ensure that all the other modalities are harmonized within this language framework. Okay, let's move on. After the multimodal encoders, now next one key technique is called the multimodal signal tokenization. While some MLMs don't always rely on the tokenization, the current trend is that many will consider tokenization. Which quantifies the multimodal signals instead of directly encoding them into a continuous embeddings. Okay, so this is seed models tokenization, which has been applied to qualifying image data. Also, any GPT that describes both the audio and image through a tokenization. Video points apply tokenization for video data. And for the visual, I mean, when I say visual, which includes both the image and video. So for the visual tokenization, most approaches represent multimodal signals as discrete tokens within a code book. Okay, so the advantage are, first of all, supporting unified multimodal signal understanding and generation. There's a second merit, which is facilitating an auto-regressive next token prediction framework. I'll give some more details next, but not here. So for other modality like audio tokenization, there are two methods. Yeah, let's quickly go through that. One is speech tokenization, and one is sound stream. Okay, next is another crucial concept of projection at the input side. So like how to connect the multimodal encoder representations to the AM, right? So the projection goes by projecting the multimodal data, for example, the image, into a language like representation, which are understandable by the central AM, right? So there are quite a number of approaches, each represented by certain MLMs. For example, the linear projection, MLP, and the resampler and the Q-former, or even some more, new techniques. So despite their difference in implementation, the purpose is very consistent. Just project the multimodal feature representation, which are encoded by the multimodal encoder to the central AM. Yeah. Here, I'd like slightly to clarify a point that the Q-former, I think many of you just heard the term Q-former. Actually, Q-former is sometimes mistaken for the visual encoder, especially by those unfamiliar with the projection techniques. So Q-former is a kind of a projection technique, not the vision encoder. Okay, so for the input side projection, here I'd like to share some more important insights. Actually, overall, different papers have different conclusions about the projection techniques. For example, from the lava paper, 2 layers MLP is better than the linear projection. But according to the mini GPT-4 paper, linear projection is more useful than Q-former layers. So I think if anyone is interested, feel free to have more discussion later. Yeah. Now we move to the core LLM parts. Actually, as previously mentioned, the LLM serves as a core of MLLM, right? Which is tasked with the understanding semantics, reasoning, and the decision making. So most of the MLMs currently rely on open source language-based LLMs, predominantly in the 7 billion size, of course, with some reaching 13 billion. I think the most widely used LLMs in the MLM community might be these two, Lava and the Vacuna. So I won't elaborate much on them here, but you can find more details information in the related LLM surveys if you're interested. Yeah. Okay. Imagine if we design an MLM only for multimodal understanding, the LLM can simply output textual response by itself, right? But in many scenarios, we want the MLM to generate multimodal content as well. And so the next introduction will focus on the technique at the decoder side. Yeah. So now let's discuss the decoder side connection and the projection, which is responsible for message passing, like converting the LLM's instructions into signals which are interpretable by downstream multimodal decoders. Sorry? Oh, of course, the text, the upper side.
Yeah, sorry, is the
yeah, I understand the question, but you can repeat for the online audience.
Thank you. Is the output text in the upper right different from the output text response in the lower left?
Yeah, the upper side, the text actually is for, they just serve as the text for the query for the user. But the upper side text response is for the multimodal decoder. Okay, so it's like a certain instruction for the as a kind of the message passing into the downstream modules. Yeah. Okay. So actually, so the multimodal connection can be divided into two types. The first type is just as the subtitle says, discrete tokens of language. Discrete token of language. So the standard practice here is for the LLM to directly output discrete text response as instructions. So you see, we have one part of the text output, which is for the user, for the user, right? But what I said here, the text response is for the downstream modules, right? Which is serves as instructions to call the downstream modules. Yeah, I mean, which will be passed to the downstream decoders. Yeah. So the advantage here. Oh, sorry. So the advantages include the, so this kind of discrete language. I mean, the text response. First of all, it can ensure actually a high performance lower bound, because when you use the text to pass the message, to pass the instruction, is actually is quite reliable. So the lower bound is kind of high, but besides, it is quite more efficient because no additional tuning is required. But also it has a shortcoming. For example, actually it is limited by the kind of inability to achieve end-to-end tuning. Also, the performance upper bound is actually limited since some modality, mark my words, some multimodal signals cannot be optimally conveyed through text. Okay, let me explain a little bit more about this point. Okay, just let me finish this slide. I will explain. Okay, so there comes the second type, message passing via the continuous embeddings. So the idea is passing the message from LLM to the downstream decoders via kind of soft embeddings of signal tokens rather than the discrete text. Okay, so intuitively, the embedding representations are able to carry much richer the modality specific features than the discrete tokens. Yeah. Besides, this also enables end-to-end tuning, right? When I say end-to-end tuning, I mean you can tune the LLM together with the multimodal decoder. Yeah, right. They can tune together. But if we're using the first type of the text response, the discrete type, actually here the gradient is stopped here. Okay. For example, for the image generation, let's go back here. Yeah. For example, for the image generation, the first type of a discrete text might fail to precisely express the visual spatial relation semantics features if we are applying such kind of technology in the region generation scenario. Okay, let's consider a real example here. For example, we ask LLM generate an image with this instruction. Say, there were originally 7 apples on the table, but I ate 1. Then how many apples are left now? Please generate a picture to describe the result. So, okay, let's check the Hugging GPT. So it utilize the text instruction method to invoke the external stable diffusion with this caption. 6 samples left on the table. But you see the resulting image actually is incorrect, right? Why? Actually, this is because the Stable Diffusion is naturally not that good at interpreting the numeration, the numeration into a visual signal. Yeah, but we use the continuous visual signal embeddings for instruction passing. For example, if we use one type of LM called the NextGPT, we should actually take the second type of the message passing manner, and the result actually can be better and robust because, as I said, through the continuous signal embedding, some kind of modality specific features can be smoothly passed into the downstream decoder, right? Okay. Actually, there is a third method. I just said two kind of method, but there is third method via the code books. So quite similar to the input side tokenization process I just mentioned. So this type of method is to let LM generate the special tokens ID and then pass to the downstream visual decoders. As I showed here, the code books discrete IDs is pretty much like the when we do the NLP task, it's like the word tokenization ID. It has the vocabulary, but here the code books we are designed for the visual. So the code books are discrete IDs. By further de-tokenizing them into visual representations, the decoder, such as VQVAE, will generate the image. Yeah. So compared with the above second method, this type of technology has one more very merit, that it supports autoregressive multimodal token generation. This is quite crucial in the unified architecture of MLMs, because right now we have the LM, I mean the language-based LM. We train the LM using what? Using the next token prediction, right? It's kind of autoregressive process. How about if we unify other modalities with the same manner? For example, the vision, we just represent the vision into a discrete token, like with the code books, and then we can, pre-train such kind of MLM in a very unified manner, right? And so we can do this, do the autoregressive manner, like the next token prediction for the region. Yeah. Well, for the generation part, text generation, well, LM naturally support direct text generation. Okay, let's go. For the multimodal generation, there is a first type of generation, like with diffusion models. For example, with the above continuous signal tokens, combining with the diffusion models, the system can generate images, videos, or audios. Here, NextGPT just, as I said, NextGPT is one of the MLM which just takes this type of manner. Okay, same manner for the audio generation. We have the speech diffusion and the audio diffusion. Okay, the second type of a generation is with the code books, which is with the VQVAE or say VQ-GAN. In this type of a setup, the MLM's encoder on the input side and the decoder on the output side together form a variational order encoder, which is called the AKA VAE, right? Here, signals are encoded into the latents and quantized and then restored via the decoder. Also, the generation of code books tokens is done in an autoregressive manner, and then fit into the decoder for signal reconstruction or generation. Okay, about we just go through the overall techniques for how to building a MLM. Actually, I do this tutorial in a very general, high-level picture, right? Okay. So this is very friendly for beginner. Okay. Let's now move to the section 2, modality and the functionalities, where we answer what are MLMs capable of. As I mentioned earlier, there are many modalities to manage. Generally, it's logical to aim to cover as many as these modalities as possible in MLMs. So in current research, most of the common modalities actually includes language, vision, audio, and 3D. So within the vision category, so this generally means actually images and videos. Yeah. So given this point, I will mainly focus on introducing the MLM on these modalities in the subsequent slides. Okay. So I mean, this 4 or 5 modalities are the main focus. Okay. So I just made a summary to all existing MLMs according to their modality support and the ability of only multimodal perceiving or simultaneously multimodal perceiving and generation. Yeah. So I will introduce each type mentioned here one by one in the following sections. So I won't describe this table repeatedly. But I think it's necessary to declare a point, due to too big number of MLMs, it's not possible for me to introduce every single model. So I will outline the main features of each type and provide a brief introductions to one or two representative MLMs in each type. Here, I'll stay for a few seconds. Okay. So as the most basic version and also the earliest appearance of MLMs, the models in this category build upon LLM by incorporating the understanding of image at the input side. I mean, so actually the first type of MLM actually occurred in 2023, I guess. And so at that point, the MLM can support understanding, not just the language, right? Also the image. Yeah, that's a very interesting at that time point. So the basic idea is to integrate a visual encoder onto MLM. So following the approach I just described in the last section. Yeah, really a lot of MLMs emerged in this category around 2023. Among all these types of MLMs, I think these 4 models might be likely the most representative ones. For example, Blip2, Flamingo, and Lava, and the MiniGPT-4. Really. Yeah, I think there's one MLM in this category that stands out as a particularly different one. Fuyu. Unlike all other existing image-oriented MLMs, so Fuyu processes the image data without a visual encoder. That's really something, and instead it directly inputs the image patches into the LM for interpretation together with the central LM. So it treats the language and the visual equal, right? So I consider this way to be a very interesting direction for future exploration, because right now most of the MLMs are actually built on top of LLM. I mean the language-based LLM. Actually, everything is based on the language intelligence. But I think, actually, if think about the infants, when we are baby, we can learn the intelligence, we can learn things from visual signal, right? Actually, we cannot speak any language. All right. Next up, MLMs that can understand the video data. So similarly, they achieve this by incorporating a video encoder, enabling LLM to comprehend the video signals. Sorry, due to the limited space, I'll list only a few representative video LLMs here. Here I've provided the architecture, the diagrams for two video LLMs, including the video ChatGPT and the video Lava. Unlike encoding images, encoding videos should pay more attention to the modeling of the dynamic temporality of the video. Yeah. So please refer to the video LLM survey paper for more models and details. Okay, for 3D perceiving MLMs, the approach is quite similar. It's very similar. They incorporate an external 3D encoders to enable them to comprehend 3D or point cloud data. Representative models in this category, including the 3DM, point LM. So for the audio perceiving MLMs, including audio signals can cover various types, for example, general sound, specific speech, and even the music. Similarly, for incorporating the corresponding encoder and applying the projection, LLMs can understand the audio data. Here, I've showed the structural diagram for two models. Let's quickly go through them. Sure. For this paradigm, as you can perceive, as you have already perceived, wide range of other modalities perception capabilities can be integrated into the LLM, right? Resulting in a X perceiving MLM. So if you want, you can rapidly construct the X MLM in the name of you, just real quick. So for instance, in the biomedical or healthcare domain, there are numerous models and research works available. Similarly, there are numerous MLMs in various fields, such as the molecular and the chemistry, graph, and many others. Okay, so the discussion above concludes the exploration of MLMs that solely support understanding single model scenarios, right? Whether image, video, or 3D, audio, etc. However, researchers in the MLM community have discovered that just focus on understanding modality, one more modality is far from sufficient. Actually, you see, MLMs needs not only to understand the input multimodal information, the input, but also has the need to generate information in that modality. So, for example, for the syntax painting and the text to vision generation tasks, right? So those tasks need the MLM to generate multimodal content, not only to perceive the multimodality and in a response of text. So gradually, MLMs with multimodal perceiving and the generation capabilities have emerged. Firstly, for images, they are representative models capable of taking both text and image as input, comprehending the semantics, and then generating both text and the images. For example, the GIF combines the stable diffusion with the embedding to achieve image generation. And the MU, also including the MU2, second version, which generate code books through the auto-regulation. So here, if I say code books, you will not feel unfamiliar. So yeah, which then followed by our image generation. Okay, for understanding and generation of video, yeah, there are also some models. So the GPT-4 video achieves video generation by directly generating the pure text, which serves as a kind of the instruction, right, to call the various external modules for video generation. Yeah. So video points, on the other hand, utilize an autoregressive generation approach, leverage the megabit decoder to directly generate a video. Okay. Similar story for the audio modality operation. Okay, just stay for 1 minute. 1 second. Oh, for instance, the speech GPT uses an audio encoder decoder and outputs audio content in an autoregressive manner. And actually, it's insufficient to consider support for only one modality, whether it's understanding or understanding plus generation. One modality, one non-text modality is not enough. Oh yes, here text is a modality inherent to the AM. We don't count it. So in realistic scenarios, modalities often have strong interconnections simultaneously. For example, you see images and videos often concur, right? And often video contain audio signals, right? Furthermore, there are some need to consider any-to-any modality interactions. So it is often necessary for MLMs to handle multiple non-textual modalities at once, rather than just one single non-textual modality. So first, let's check the combination of text plus image plus video. There are several MLMs that simultaneously support these three modalities. Here, I should just showcase the chat unif model. So the implementation approach is quite simple, just adding more corresponding modality encoders or decoders to the central LLM. Okay, and for the combination of text, image, video, audio, the approach is very much similar, but there are more MLMs in this category, really more. So for example, the Macau LLM, it integrates image, audio, and the video encoders, and then do the alignments before feeding into the LLM. Okay, indeed, integrating a limitless number of modalities is practically endless. Can you feel that? So some research directly focus on constructing any-to-any MLMs. So this is awesome. So this category is closest, to the paradigm of AGI. NextGPT is just the one, which is a pioneer work in this category. Which introduced the concept of any-to-any MM for the first time. So this architecture achieves a powerful functionality and is parameter efficient alignment learning strategy. Also demonstrate kind of novelty. Okay, I said I want to stay too long for just one single modality, right? MLM. After expanding support for the modalities, researchers in the community began considering how to enhance the depth of MLM capabilities. This can be described as achieving fine-grained capability of MLM. Currently, this idea has only been implemented in the vision MLMs. So when considering the vision data, previous work focused only on the instance level overall understanding. For example, I'll give you an image. Just tell me what everything about the image itself is a instance level understanding. But this often leads to inaccurate vision understanding and even multimodal hallucination issues, right? For example, if you only can handle a the instance level image under comprehension. Actually, you will miss a region, a certain pixel of the image, because you do not do this work in a very fine-grained manner. So to address this problem, it's necessary to equip MLMs with a pixel level, pixel wise region perception. Okay, so such a fine-grained capability can be reflected in many tasks. For example, the grounding, the visual grounding and the image segmentation, the editing, and then even indenting. Of course, I know if you are not familiar with the computational vision topics, is a very hard topic. Okay, without further ado. Currently, based on the support for image and the video modalities, this can be divided into two categories. One is for the image, one is for the video. So let me walk you through these MLMs. Surely, there are already many pixel-wise MLMs for images. Generally, users input an image, potentially specifying a region. Yeah, and the M outputs content based on its understanding, grounding the region content to the specific pixel level regions of the image. And here I'll showcase the next chat and the GLAM models. Actually, we can continue to categorize them, these MLMs based on different perspectives. For example, first I can consider pixel level awareness, whether at the input side or the output side. We can classify them as follows. For example, some models only support fine-grained pixel awareness at the output side, but some can provide in the fine-grained perception in both the in the output result, and also accept the fine-grained input from the user at the input side. For example, you as a user, we can indicate the specific region, the pixel region, or we can input a coordinates, which are the region coordinates. Okay. Then, based on the granularity of the pixels, we can further classify them as whether supporting the bounding box coordinates or just directly utilizing fine-grained mask level segments. Okay. Finally, we can classify them based on whether they support user input interactions. For example, some cannot support user interactions, and some can support user, like I just said, specifying regions through inputting a bounding box coordinates. Also, some models, the most ideal type is to directly support users inputting the sketches and doodles freely, right? Okay. So for pixel level MMs for video, there are some models. For example, the PG video lava can output dynamic grounding, even segmentation for objects within a video by understanding the video. And also the motion epic achieves fine-grained video grounding by integrating video scene graph representation. Okay, so it seems like everything is still fragmented with various different levels and the granularities of support, as well as support for different modalities. And so the question is, can we unify all of this? Okay, the publication of Vision answered this question. Vision. So firstly, we observe that the existing MLMs for vision tasks, the image and the video, suffer from uneven coverage of various fine-grained vision task clusters, right? Also, they cannot simultaneously support both the image and the video, which are actually two homogeneous vision modalities. Okay, then the images of vision, the vision, which completely address these issues. So vision represent the first unified pixel level vision MLM, consolidating tasks such as understanding, generation, segmentation, and editing in the vision domain. So it lays the foundation for the for the ultimate form of the next generation universal vision generalist. Okay. Okay, the model architecture is like this. Of course, considering the time limitation, it's not possible for me to expand more details. So please refer to the paper for more details. Okay, I think I'll let my partner Yuan Yao to take the control for this part. Yuan Yao here.
Okay.
Hi, are you there?
Okay. Yes, I'm here.
Okay.
Thanks all for the introduction. Okay.
I'll escape and let Yuan Yao take control.
Okay. Thank you, Fei Hao, for the introduction.
Okay.
I'm Yuan Yao, and
Yeah.
a postdoc from the National University of Singapore. And I will briefly introduce two topics, including the multimodal, multilingual multimodal LLMs, and also unsigned MLMs. And for the first, LLMs, multimodal LLMs, currently they are most strong in English, but weak in other languages. And remember that we have many, not only English, but over 7,000 languages in the world, and we want our MLMs to serve the multilingual community, to serve the global wide people. And but currently, this is not a very good situation, because for other languages, the multimodal data, they are limited in both scale and quality of image text pairs for non-English languages. And and even if we have sufficient data available, there will be also a very huge computation cost if we want to train a multimodal large language model for each language. And for the figure in the bottom, we can see that even for Chinese, which is considered traditionally considered to be a language with rich resources, and their image text pair data quality is not very good, and most data their relevance is not so good. So we cannot train a very good Chinese multimodal large language model. And speaking of this question, a very natural question is, why not use a machine translation pipeline to translate the English output of multimodal large language models to other languages? And so there are several reasons. So the first reason is that if you want to use a machine translation pipeline, you will need another model for translation. So for a good performance, maybe you will need another large language model of the same size for translation, and that will double the computation cost and the delay of the whole system. And another thing is when we miss the visual context, that will lead to incorrect translation in this pipeline. And also, this is not an elegant way to AGI, because we want a single model to master all the capabilities. And this is also shown to be doable, achievable by recent works. So next slide, please. Okay, thank you. So currently, a good way to achieve this capability is by generalizing multimodal capabilities to non-English languages using a multilingual large language model as a pivot. So the basic idea is very simple and intuitive, just like human learners. So if you are an English native speaker, so during your childhood, you are actually, when you learn English, you are actually do a multimodal alignment by aligning the English symbol to the visual signals. So, for example, you will align the cat symbol to its visual signals. And when you learn a second language, such as Chinese, you can do this in a pure text setting. For example, you can just align the Chinese symbol corresponding to cat to its English symbol, and then you do not need to align every Chinese symbol to its visual representations. For the human learners, we can automatically achieve this generalization. So we think it is also doable for large language models. And the basic idea is the basic practice is also very simple. We can achieve this multilingual alignment by reusing multilingual LLMs. So their representations for different languages, they are well aligned. And for the multimodal alignment, since we only assume to have very rich English image text pairs in high quality, so we can do only extensive pre-training on English image text pairs only for this multimodal alignment. And so this will serve as a high resource pivot to align other languages to the visual representations. And by this generalization, we can achieve very good performance. And so next slide, please. Okay, so if you train the model in the above mentioned fashion, you will find after pre-training the English pre-training the pre-training on English image text pairs only, the foundational capabilities can be well generalized to other languages already. For example, if you use Llama as a backbone to pre-train it extensively on English image text pairs, and when you and also do the SFT process in English image text pairs only, and you will find when you ask a question about an image in German language or other languages, in fact the model can correctly answer this image in very good semantics, but the language is not in German or other language; it's in English, and this is very this phenomenon is very interesting. It shows that the model as a foundational capability, they can understand this multimodal semantic in other languages, but their output language is not well aligned. So you can align this output language, switch this language using a very lightweight SFT. So next slide, please. Yes, and so to switch the output to the target language, a lightweight SFT is sufficient. For example, you can translate only about several thousand SFT data for each target language to align this target language. And this generalization actually they behave very well and beyond our expectations. So it can, for example, they can generalize to not only to visual concepts, but also the cultures. For example, in this example, the model trained this way can describe the image in a traditional Chinese poems. So so during their training, they cannot see such data. So so such generalization can also deal with cultural difference. Okay, so next slide, please. And this is also adopted as a common practice nowadays. So many strong multimodal large language models featuring multilingual capabilities adopt this practice. For example, the LavaNext, the EVL, and the MiniCPM series. So when you want to build a multilingual multimodal LLMs, you can consider to do this way, and this is very cheap. For example, for the latest MiniCPM Vision 2.5 version, so so this model uses Llama 3 as a backbone and do this paradigm in a very large scale and can support over 30 languages simultaneously in a single model. So it can achieve promising performance. Okay, so next slide, please. So that's about the multilingual multimodal large language models. And the next topic will be the unsigned multimodal large language model. So large language models, when they are really large, they can show astonishing performance. And but currently another trending is happening. So unsigned LLMs, they show good potentials. So by unsigned, we mean the unsigned devices such as mobile phones and personal computers, and also maybe iPad and devices on the cars. So these end-side devices, so they require the models to be small, typically about around 2 billion to 5 billion or 7 billion parameters. And this also depends on what device we are talking about. So just around this level of parameters. And this is, for example, mini CPM is a good example of this. So by properly training and so a smaller LLMs, they can achieve a comparable performance to larger models. Okay, so next slide, please. And this trending also shows very promising potentials in multimodal large language models, and many end-side multimodal large language models are emerging recently, and their performance are growing in a very rapid speed. So their performance can matching larger language models, and representatives include mini CPM Vision, DeepSeek, and mini Gemini, Bunny, and other very good models. And taking the mini CPM Vision as an example, so around 2 billion parameter MLM can match the performance of larger MLMs such as COLING with 17 billion parameters. So that will give us better potential to employ them on the devices. So next slide, please. And by deploying the MLMs on the end devices, it will give us many benefits. For example, if you can deploy the multimodal large language model on the mobile phone, it will give you better efficiency and also better accessibility, since almost everyone will have a mobile phone, but not everyone will have a server in its home. And it will also give us better privacy protection, since we do not need to upload our personal data to the central server. And the application driven by an end-side multimodal large language model can also well functioning even without network connection. So that will be better on devices on car and automatic vehicles. And so for the right side, this is a real time recording of a demo of mini CPM Vision. So it can give currently about 2 billion parameters will give very good speed, the interaction speed on a mobile phone. So I think that's all for the end-side multimodal large language model. So maybe you can take back the control.
Okay, thank you, Yao. Okay, I'll
thank
take
you.
control. Thank you so much. Okay. Oh, we make it to the final section. Okay, so think about we go beyond MLM, what to do next, and how far from MLM to the AGI. Okay. Firstly, we believe that MLMs must demonstrate strong performance across various evaluation benchmarks to claim a closer proximity to AGI. Currently, there are some commonly used benchmarks. For example, MME focuses on the image modality and encompasses VQA task with 14 multi-choice question. LVLM eHub supports a greater number of tasks, including 47 types of data and 6 different cross-model ability. MMT bench further expands the breadth of evaluation. It includes evaluation for 32 multimodal capabilities, 162 test sets, and cover images, videos, and point cloud modalities. All right, ladies and gentlemen, I now have 3 questions of Seoul. Question 1, can we simply assume that stronger the performance of MMs on these benchmarks, the closer they are to achieve AGI? And question 2, can it be said that the more modalities and the task types supported by MLMs, the closer they are to AGI. Question 3. So how should MLM evolve to ultimately achieve AGI? Okay. I think the terminology AGI is too broad. Let's not say AGI. Let's say human level AI. I guess it should be more suitable. So let's consider the key points from MLM to human level AI. First, we believe that the ultimate form of MLM will evolve towards being more generalist. It gotta be a generalist. So human level AI will be a multimodal generalist. Second, human level AI as this generalist will support as many modalities and functionalities as possible, right? And third, and most importantly, human level AI will have strong generalization ability, capable of learning from limited data and modalities, and can do the abductive reasoning, like can make decisions from limited information at hand. So, okay, now we consider how to evaluate MLM generalist. So to do this, we propose the levels of multimodal generalist. So this table illustrates the hierarchy of MLM generalist. Okay, we categorize different models into 5 levels. It's like the process of climbing a ladder. We rank existing in the future, maybe future incoming MLMs, encourage them to achieve higher levels and thereby bringing us closer to the goal of human level AI. So the first level, level 0, corresponds to the position of separate specialist in the most of previous research. So these models are trained on the specific data sets and the tasks of one certain modality. For example, the VQA on the Microsoft COCO, right? And there, they exhibit a strong capability. So this is for the separate specialist. Moving on to the next level, level 1, called the generalist of comprehension, where the specialists from level 1s are connected to the MLM as the intelligence decision makers, which enables multimodal comprehension. So level 1 MLMs can understand the multimodal data and provide the textual answers. So supporting the texts like classification, QA, etc. So the feature of this level is the generalist. So this levels of generalist is weaker than the individual specialist. This makes sense. Why? Because actually most of the existing MLMs, they just cannot beat the SOTA specialist on a single task, a single data set. So this is a fact. So most of them actually lies at the level 1. Now advancing to level 2. The generalist at level 2 requires level 1 MLMs to achieve both multimodality and the multitask synergy in general in the generalist of comprehension. So you see, while preserving the core capabilities of LLM and the sharing cross-model and cross-task invariant features, it has to achieve the multimodality and the multitask synergy, the keywords synergy. Task and modalities supported are similar to level 1, but the performance should be much stronger with the generalist surpassing the individual specialist. Because what? Because it is benefit from the synergistic effects among different modalities and the tasks. Then from level 2 to level 3, the ability to generate modality content is included, not only to comprehend, but also comprehend plus generation. So, so this will unlock more tasks such as image and sound generation, region segmentation and editing, even any-to-any modality generation. So this level demands that during the generation, the generalist can reconstruct the necessary multimodal detail clues from the LLM output. I mean, the multimodal tokens at the decoder side. Actually, the community is currently advancing towards level 3. And even some MLLM have already achieved any-to-any capabilities. But at this level, the generalist is still weaker than the individual specialist in cross model generation. So finally, we expect to reach the final level 4, where the generalist is not only achieve both the comprehension and the generation, but also come with a strong multimodality and a multitask synergy. Although supporting similar tasks and functionality as level 3, level 4 can ensure the generalist is way stronger than the individual specialist due to the synergy. I mean the different modalities and the tasks, as well as the comprehension and the generation modules, can mutually assist each other with synergy. So that's the key. Everything within the generalist, I mean the MLM, can collaborate. Yeah, the data and the features can flow. So that's the key. The generalist at this level must process, adaptive reasoning ability, and can be capable of performing task prediction by just learning from a limited data modality. Achieving this level of a generalist will be a significant turning point towards realizing the human level AI, I guess. So let's look back to the MLMs we already have right now in the community. Actually, most of them that only come with multimodal comprehension ability stay at level 1. Maybe very few is capable of level 2 with the synergy. Very few. But I think right now, most of the MLMs cannot really beat the specialists at each domain and each benchmark data set. And also, there have been a very good number of MLMs that support both the perceiving and the generation. So this should hit the level 3. But even in level 3, different models might have a different capability. For example, some support more modality support coverage, while some support deeper and wider tasks. Okay, after all, I think our ultimate goal is to achieve the level 4 and beyond. It should not be surprising or very tricky to combine all existing different specialists, combine them together, integrate them into LLMs. But how to achieve cross-model and cross-task generalization ability, as well as the adaptive reasoning with the 1 + 1 larger than 2 effect, that's the key. Think about the ChatGPT, right? Is the most understanding model at the language side. I think in language side, such abductive reasoning ability to a certain extent has already been achieved. Well, I'll say that maybe the definition of these levels is or ongoing work, and the current version may not be comprehensive and sound enough. We are still refining, but whatever, let's work together to achieve a higher level of generalist towards the final goal, human level AI. And what's next, or say what can we do towards that goal? here I'd like to share some key directions I consider quite important as a very near future work. Firstly, we haven't fully explored the modalities at both the breadth and the depth perspectives of the task support. So at the modality perspective, most of the current MLMs focus on integrating vision modalities such as the image and the videos, with some also considering audio, surely. But other many modalities should also be included and considered, as human perception of the world covers a vast array of modalities. Even the current NextGPT, that one only supports 4 modalities. So there are still quite a good number of modalities to go, such as code, 3D, document, touch, smile, etc. You name it. Also, the task at the task perspective, we should go deeper. Currently, MLMs for task support varies. For example, vision-based MLM, vision, I just mentioned, vision has focused on unifying images and video processing under the scope of a pixel-wise task modeling, ranging from the low level to the high level. So it's a good workflow. The next step should further expand the MLM in supporting the task at the deeper level, right? Okay, the second angle is quite more concrete, and which is about how to achieve stronger multimodal generation ability. So right now, MLM research is rapidly evolving from the multimodal comprehension only to the multimodal generation. However, the current capability for the multimodal generation still requires further enhancement compared with the multimodal understanding capability. So one specific challenge lies in achieving a more elegant end-to-end method for the modality to modality conversion. For example, XGPT uses soft embeddings to connect the backbone diffusion models to generate as many modalities as possible. But actually, this method does not support a completely end-to-end full stack training, actually. A better approach could be based on the multimodal tokenization. Yeah, I've already demonstrated that. And transitioning to an, more autoregressive generation manner, like how we do this for the language. Okay, so here is a takeaway idea. A hot trend in this topic currently is about achieving better video generation through more robust video tokenization, especially when supporting both images and videos. There may be a need to more carefully model the spatial aspect of images and the temporal dynamics of the videos. Yeah. So the last angle is about maintaining multimodal multitask synergy. That's, I can say, the most important thing we were gonna do. As defined in the above levels of MLM, the table, achieving a stronger MLM and potentially reaching the human level AI, it is so important to achieve the inner synergy in the generalist. So this aspect is particularly worth exploring. So let's think about how to achieve stronger generalization ability by mastering the adaptive reasoning. We humans don't need to see every case during training, right? But can do the analogical reasoning, right? So I'm just wondering, can we achieve that singularity? I mean, the emergent phenomenon by end-to-end training the MLMs with the super large data, the way as in training a language-based LM like GPT. So yeah, this is an open question. Okay, we hit the end of this part. So let's quickly summarize everything in this keynote slides. So we've just give a tour on how to construct an MLM with what technologies we need. So which is the section 1. And then we summarize almost all the existing MLMs in detail. I can't say no, it's not in detail. We just stay at the very high level, right? And finally, we present the levels of MM, generalist hierarchy, paving the way for future efforts in this topic. And yeah, thanks everybody. I think I've just finished this part, and maybe let me see. It's already over time, so maybe we can have one or two questions, please. Okay, please. Fellows, we can we can answer your questions. We have a team, right? We can answer your question. All of our team member, please.
Thanks for your talk. I just had one doubt regarding the slide 91.
91.
Where you gave the
so
different
concrete.
levels.
91.
Yeah.
Oh, this one?
Yeah, I didn't understand why the key characteristics, it goes from weak to strong to weak to strong, because then it means that we already have level 2, like we might not have level 2, we might not have reached level 2, but might have already started working on level 3, because level 3 is a bit not that stronger ability, right? So I wasn't that sure.
Okay. So I assume you are asking if a model is at level 2,
Yeah.
they have the ability to being level 3.
So like I didn't understand why have you reduced down the key character, the generalist is stronger than individual specialist,
Okay.
to the generalist is weak than individual specialist in level 3.
Okay, it's just our ongoing work about how to defining the the levels of current MLMs. So why we so your question is about there is a there is a leap from the level 2 to level 3, right? Okay, according to the definition, level 2 means sorry, yeah, level 2 means within the category of multimodal comprehension type. And so the level 2 requires the MM to be synergetic, right? The okay, why? So you want to ask why define the level 3 based on the level 2. So the level 3, from level 2 to level 3, one key capability is to generate multimodal content. Not only the generalists have the synergy ability. Yeah.
So, yeah. So in that sense, we can already achieve level 3 without achieving level 2. That was my whole point.
Oh, yes.
Right. Okay.
Yes.
So it's not a direct, it's not a hierarchical thing.
No.
Okay.
No.
Okay.
But sure. So we in the next version of the asset is our ongoing work that we will release later, and we will still refine this definition. But the general idea should be very meaningful. We evaluate the MM not only on its performance, the task performance, but also whether it is synergetic, right? The synergy ability, yeah, and also the reasoning ability, the generalization ability, yeah.
Okay.
Please stay tuned to this work. Yeah.
I had just one more small question.
Okay. Okay.
So regarding the language bind and image bind thing, so I wasn't like, because if we are converting everything, like let's say the audio using WEF to VEC or something into the form of, like if you are tokenizing these things, both the audios, the vision, the images, the text, then why is it that we are saying that it's language bind when like is this token something that we are still saying it's more like language based because the image are also getting converted to tokens. So yeah, I didn't understand that part. Like when we say that LLMs are the backbones, but we are also converting the images to tokens and then we are training them on that. So
Okay,
why are we calling them languages?
let me go back to the pages. So you are saying why we align the all the modality representation into an image or language?
Yeah, I mean, like, but so these terms, image bind or language bind, like, are we just saying that when we are converting, let's say that we are taking an image and using an encoder, and then somehow we are tokenizing it or something?
Yeah,
like those,
yeah. So
then are we saying that those tokens that we are generating from them, they are equivalent to some language? Is that how we are imagining them when we say it's language bind?
Also, if we're using the image band or the language band as the multimodal encoder, we will not using the tokenization technique actually.
Okay.
Right. As I said, that actually the tokenization technique is not necessary unless we're integrating the VQA technique actually. So if we're using the image band or the language band, you just project the unified representation into the AM. Yeah.
Okay.
Okay. Thank you.
Okay, thank you.
Okay. I'm afraid we are running out of time. Okay. I guess we will need to move on to the next part. Okay. So next, Fu Xiaoliu will be the presenter to give the section 2, the part 2 about the multimodal instruction tuning part. Please give a second.
Okay.
Okay, Fu Xiaoliu, now you have been the host and you can now share your screen.
Yeah, sure. Thank you. Thank you, Hua. Can you see my screen?
Just wait a second.
Oh, yeah, sure. No
Let
problem.
me stop sharing.
Oh, yeah.
How can I?
Yeah, I'm in my first page.
Please proceed to sharing your screen. No, sorry.
Let me reshare. Let me try.
I need the technical help, please.
Okay.
So the audience in this room cannot see your screen.
Oh, yeah.
Yeah. During Fu Xiao's tutorial representation, there will be a 30 minutes for the coffee break. I'll later give it. Oh, so let's just. No problem. Okay. I guess how about let's go for the coffee break because it is a time for coffee break, and then we 30 minutes later we'll continue. Okay. Thank you, everybody. Yeah.
Okay. Oh, thank you, Hao. Thank you. Okay. Hello, everyone. My name is Fuxiao Liu, and I'm a third-year PhD student from the University of Maryland, College Park. And today I'm to give a talk about maybe like multimodal instruction tuning in multimodal large language model. And in this talk, I will cover the content like the motivation for the multimodal instruction tuning and the popular multimodal large language model instruction tuning framework, and also like the data for the multimodal instruction tuning, and also like some challenge, including the hallucination and some like mitigation method to solve this kind of problem. Okay, like why do we need like the multimodal instruction tuning? So generally speaking, I think the main benefits of multimodal instruction tuning is that it just change from the single purpose to general purpose. I mean, like for previous like traditional computer vision model, they are focused on like the one task. They can't follow the diverse of human instructions. They can only do like the segmentation or maybe like the object detection or maybe like image captioning. So this will limit the potential, to the potential of this model to like the unseen task. So, but for the multimodal instruction tuning framework, the benefits is that they can follow human instructions, so they can solve different tasks. Just like the example right here, you can see for the traditional computer vision model, for image capturing task, they can only solve like the generate image capturing, but for the object detection task, they can only detect the dog in the image. But for the current multimodal instruction tuning framework, you can say give an image and give like the instruction of human, like maybe describe the image describe image. So the model can generate the caption like the image feature a large brown dog and a small gray cat sitting together in the tile floor, and also like a different instruction like detect all the objects with bounding blocks. So for the instruction tuning model, it can generate like there are two objects in the picture, including like one bounding box and another bounding box. So you can see the benefits of like the multimodal instruction tuning framework is like is more obvious than the traditional computer vision model. So, what are the recent popular multimodal instruction tuning framework? In this section, I will include like the framework and the training paradigms, and also like the input template for the multimodal instruction tuning framework, and also like the evaluation pipeline.
Okay. Sorry. Hello. Fuxiao, can you show your head? I mean.
Yeah.
One. Thank you. Yeah.
Oh, one. Sorry, I forgot.
Yeah, so that everybody can see you.
Okay. So let me. Oh, you can see me, right? Okay. Yes, sorry, I forgot. Yeah. Okay. Cool.
But why the screen is always enlarged? It's in the Zoom.
Yeah, I think it's good. It's good right now, right? Yeah, I can see your screen.
Okay, please go on.
Oh yeah. Yeah, let's continue. You can see like in this slide, the pipeline of like the multimodal instruction tuning include two parts. The first part is like the instruction tuning data set generation, and the second part is like the vision instruction tuning framework. And for the popular multimodal large language model, it includes like the GPT-4, Lalava, or Lalava Nest, or maybe like Lalava UHD, or some other models. I will talk about more details of the visual multimodal instruction tuning framework in more details. Generally speaking, the multimodal instruction tuning has two stages. In the first stage, it's called like the pre-training stage. The purpose of the pre-training stage is to align different modalities, which can provide the word knowledge for different modalities. The second stage is called the instruction tuning stage. The purpose of this stage is to teach model to better understand the instructions from the user and fulfill the required task. And in the first stage, we usually like only train the adapter for the video encoder, or maybe for different modalities. But in the instruction tuning stage, we usually open the parameter for the large language model adapter, and maybe for the video encoder, or maybe like the encoder for different modalities. Here are some like popular multimodal large language models, like maybe MinGPT-4, Lalava, and Unplug OWL, and also like the Cosmos. And you can see like for MinGPT-4, the training paradigm for MinGPT-4 is like in the first stage, it will only like open the adapter, and also like in the second stage, it still like keep the large language model part and also like the video encoder part first. But for the Cosmos framework, it just open both the large language model part in both stage. But for the Lalava, it only it will only train the adapter in the first stage. But in the second stage, it will train both the large language model part and the adapter part, but keep the video encoder part the freeze. And then for the last one, Unplug series model, it will like maybe it will open the gate for the video encoder and adapter in the first stage. But in the second stage of the fine-tuning stage, it will freeze the video encoder part, but open the gate for the large language model part and also like the adapter parts. How can we after we got we have data, and how can we put the data into the model? So we need to have like the template to absorb the data, and you can see there's one example right here. Like below is the instruction that describe the task. Write the response that properly complete the request, and then you need to there's a slot for the instruction, and then there's another slot for the different modalities, like maybe the image, video, audio, and also like maybe the context test. And then you need to also like add the response, maybe the answer right here. And there are also some like example right here. The instruction may be like describe the image, and the response may like the detailed captions for the instruction. And then in the instruction maybe like the detect all the objects, or maybe like modify the picture into the sketch style. And for the response, it will have like a corresponding answer one by one. Another problem comes like, how can we evaluate this kind of recent like multimodal large language model? And there are like 3 strategies. And the first one is like a human evaluation. Of course, it's, as for human evaluation, it's most accurate because like we trust human can evaluate the can look at the image first and look at maybe video first and then compare with the answer. It's very accurate, but the disadvantage is that human is always very expensive. You need to pay for them. So that's why another option comes like GPT-4 assist evaluation. The advantage of the GPT-4 evaluation is very clear, obvious. Like they are cheaper than human, and also they can also achieve the same level of accuracy as human, and also provide an explanation for their result. And you can see one example in the right. You can see there's a image with dog, with some guys surfing in the sea, and the question is like, can you help me find a dog playing with a ball on the shore? And there are like 2 responses from two models. One is MinGPT-4, and another one is Unplug OWL. And then you can see for the first model, it just say like there's a dog playing with a ball on the shore, and you can see the GAVIE means like the GPT-4 assist evaluation model, and it evaluates the answer based on 2 parts. The first one is like the relevance score, means like whether the answer follow instruction, and then the second level is called the accuracy score, means like whether the content or whether the answer align with the image content well. And the GPT-4 this evaluation gives like the only score 1 for the a relevant score for the first answer, because like and gave 10 score for the first answer, because like the answer follow instruction very well, like it says there is a dog in the image, but as for the accurate score, it gives only 1, because like there's no dog in the image. And for the second answer, like the answer from GPT-4, it says like the image is a photo of the group of 3 people surfing on the ocean, and so on. And for the relevant score, the evaluation pipeline only gives like the 1 score, because it does not follow instruction. It only like describes the details of the image. But for the accuracy score, it gives 10, because it's very it's aligned with the image content very well. Okay, and the final choice will be like the quantitative metric evaluation. Of course, the advantage is that it's much cheaper. Is much cheaper than both the human evaluation and the GPT-4 assist evaluation. But the disadvantage is also very obvious. Like, let's say here's an example right here. You can say you have to you need to change the question of the instruction into maybe like the multi-choice QA question format, or maybe like the yes or no question. So in this way, it will limit the evaluation scope and also the ability of the multimodal large language model. Okay. I also like summarize like some recent popular benchmark for the multimodal large language model evaluation. You can see like for the MME, which is for the comprehensive evaluation for both the perception and the cognition. But for the evaluation method, it's like only yes or no question. But as for the hallucination bench, it's the GPT-4 assist evaluation, and it's also like target for the multimodal multimodal large language model hallucination. And for the MMC benchmark, it's target for the chart understanding. Okay, here are some other models. Okay, you can look into this paper for more details. Okay, as for the second part, like multimodal large language model instruction tuning generation. And in this section, I will include the pre-training data. How can we generate the pre-training data, and how can we generate the instruction tuning data? And I also summarize some like recent popular instruction tuning data sets. Okay, see. And so we use the pre-training data for the first stage, like the pre-training stage. So how can we generate the pre-training data? So I summarize some like recent popular pre-training data right here, and they can be categorized into 2 parts. The first one is called the cross-skin image test dataset, and the second one is like fine-game image caption test dataset. For the cross-skin image test dataset, which means that the data volume is very large, and they got it from the website. But sometimes the caption will be like very short and noisy, so it may influence the quality of the model after you train on this kind of data. But for the second category, the fine-game image test, they always high quality, or maybe they are longer and contain more details of the image, so that the description is more accurate. And for the fine-game test, maybe the popular one will be like the shared GPT-4V, or maybe like it is for the image test, and maybe for the MSR VTT, it is for the video test. And I will also like show you some examples of this, the 2 categories, so you have a basic idea how what's the difference between these 2 categories. You can see here is the image in the left, and the 3 descriptions of the image in the right. So you can see the first part of the caption is from Coco, and you can see the Coco caption only involve the brief human-made captions on the main subject. Although it's very accurate, but the details is not enough. For the second one is from the Lalava. They just combine human-made captions and then like all the bounding box, and then put this kind of test the information into GPT-4, test only GPT-4, and ask GPT-4 to image the image content. So because they are not like they only use test only GPT-4, so the GPT-4 can only imagine the content. So there must be some like hallucinations within their data. So you can see the test in right. But for that shared GPT-4 they use GPT-4 vision, and then they design very careful prompt along with like image and put them both into the GPT-4 vision. So you can see the caption is not only longer and has more details and is more accurate. So that's why the sign-in image test data is more beneficial for the model. So after talking about the precision stage, the precision data, we also need like instruction tuning data in the second stage. So how can we get the instruction tuning data? Maybe the direct thought will be like we can use like the existing VQA data for the training. But there's one limitation right here. You can see there's one example in the right. You can see there's a chart image, and the question will be like which year has the most divergent options about the Brazil economy? And answer is 2015. Sure, it's correct, but it's too short. But like when we fine-tune our multimodal large language model, we don't want the answer from our model is so brief and so which do not have like enough details of image. So in order to handle address this kind of problem, another strategy comes called like a date adaptation, which means like we can maybe declare the short and brief for the short answers in the instruction. Maybe for the same example, we can add another instruction in the end of the question, like a short answer to this question is. So in this way, the model will learn that you need to give the answer for the question in brief. So here's like some template, or maybe we'll use for the question. Like maybe you can say the first one will be the question, and maybe, or if the answer is very short, we can also say like the short answer to the question will be, or maybe like please generate like the passage, maybe like a several sentence for the question, so the model can be instructed to generate the long answer. So it is very important for to generate to get our model to generate the length of to generate different lengths of answers based on human instruction. And the third strategy is called like the self-instruction, which means like we can translate the image into just captions or maybe bounding box, and then like prompt the prompt into text only GPT-4. You can see the example right here. You can see we first put like the bounding box information, which contains maybe the detailed bounding box number and also like the dense captions, which is about the image content. And then we also add the task description right here. Maybe like we want GPT-4 to generate maybe the image caption task, or maybe like the image semantic analysis task, or maybe like multi-choice VQA task. After that, we also add some like a generation requirement right here, which will be like come up with 20 diverse instructions of all the tasks of the different language style and accurate answers. The instruction should contain different language style, and also the answer should be less than 30 words. So, and then each task should have less than 3 instructions. And then in the final of the slide, you can see like there's an output from the GPT-4. Okay, I also this slide summarizes some like the recent popular instruction tuning data set for different modality. You can see maybe for the Lalava instruct, it's for the image test, and it uses ChatGPT generate. And for the LLM instruction, it also uses GPT-4 generate, but I think it also the modality is like the image test. For the MMC instruction, is for the chart and test, but for others, maybe like maybe IT, or maybe like the Llama, which can have different modality, maybe like image video test, and also like maybe image point cloud and test. So there are also like many other data sets. So you can search this data set based on name and feature of them. So after talking about the how can we generate the data, instruction tuning data for the multimodal large language model, and also the framework for the multimodal large language model. So there are also some like the challenge in multimodal instruction tuning. So it will be like maybe the hallucination problem. You can see for the current multimodal large language model, they are easy to hallucinating like inconsistent descriptions with respect to the associated image and the human instructions. So here is an example right here. Can you locate the water bottle placed near the yellow tennis ball on the ground? And based on, you can see I give a response of four models right here. For all of them, you can see they just follow the instructions, like the water bottle in the instruction, and combine the information with the content within the image. But actually, there's no water bottle within the image. So you can see the hallucination, the object hallucination within multimodal large language model is very common. And here is another example right here. It's from the hallucination bench. You can see I gave the same prompt for two contrastive, like the one negative image and another positive image. I mean, like maybe the general idea of maybe the content of the image is very similar, but maybe only a detailed part of the image is different. So you can see in the two images, only maybe the size of the two orange circle is different, but for the green circle, it's generally the same. And the problem is like the right orange circle the same size as the left orange circle. And you can see even for the first image, the GPT-4 will give answer like the right orange circle appears to be the same size as the left orange circle. Yeah, it's correct. But for the second image, we give the same prompt, the question, but for GPT-4a, it gives the wrong answer. Like, yes, the right orange circle and the left orange circle, they appear to be the same size. So you can see, even for GPT-4a, they may prefer to answer yes for some of the questions, even though you know the details of the image will be a little bit different. But for you can see Lalabak 1.5, you can see for the first image, it says, no, the right orange circle is smaller than the left orange circle. It's not correct. But for the second image, although it gave the different answer, it says, yes, the right orange circle is the same size as the left orange image. The answer is not. It's also like hallucinate with the content within the image. So how can we mitigate the hallucination within multimodal large language model? Here, like three, the mitigation strategy can be categorized into three levels. The first level is called like the pre-correction. Maybe like you can refine the instruction data, just like maybe for the IRA instruction, which can contain both the positive instruction and also the negative instruction. And for the in-process correction, it means like you can design a more state-of-the-art model, maybe add more maybe complicated modules in your model to solve this kind of hallucination. But for the post-correction, it can be together as a post-processing, which means like after you generate the captions or the answer based on the instruction and the image, and then you add some other maybe like object detection modules or something to see whether the content within the answer is correct and then refine and correct it. So you can see the details for the IRA instruction. You can see in IRA instruction, it contains both the positive instructions. You can see in the top part of the image right here. You can see like has like multi-choice QA object type detection. It means like the positive instruction, and the instruction in red, which means the negative instruction. The negative instruction includes like the non-exist object manipulation. Means like in the question, it will add some like the non-exist object within the question. and also like the object manipulation, which means that which means like model will also like manipulate the attributes of the existing object in the image, and also like the knowledge manipulation, which means like they will change maybe the country name or maybe like the name of that celebrity with the image. Okay, and you can see here's like some results, like if we fine tune like the Lalava or maybe like other models, and then the model will be more robust. So you can see the example right here. Yeah, the answer from the LR instruction model is in the bottom of the image. You can see, yeah, and it says like there's no object resembling the water bottle mentioned in the image. So this question is introduce a new object that does not exist in the image. So you can see the new model can correctly say there's no water bottle within the image, and then point out is like the misleading question. And also for another example, like you can see for now it's for the chart, and the question is like, does the COVID cases increase in China? But actually, you can see this chart talks about the COVID cases increase maybe in Japan. But for the, you can see for all the previous models like Min24, V1 and V2, like, and also like Lalava 1.5, they both follow instructions like, yes, the COVID cases in China, and maybe add some like imagine details and follow instructions. But for the model, we just want to on our instruction. The model just say like the image is about COVID cases in Japan or China. So you can see it's honest and say no to the instructions, like there's like there's a mistake. So and another model is the woodpepper, which is like the post correction. So you can see the example right here. You can see the output of the multimodal large language model is in the blue box, and you can see after got this kind of caption, it will use like the key concept extraction, like it will extract the key concept like the bicycle, trash bin, and also like person from the image. It can be also like maybe some other humanity or something, and then use like the question format, to change the object to maybe the key concept into question, like how many bicycles are there in the image, and like how many people image, like where the trash bin in the where the trash bin located, and then it will like use some other models to do the visual knowledge validation, and it just found like there's no person image, so it just found the person mentioned in the multimodal large language model output is wrong. So it just correct answer and then say there's no people with the image. So you can see this method is also effective. So here's the end of my talk, and I just gave like a summarization right here. You can see we talk about like the motivation of like the multimodal instruction tuning, like why we need that, because it just change the single purpose into general purpose. It can follow human instructions to deal with the unseen task. It is very important because like we don't need we don't need like one single model for one task anymore. We can just use one general model for all of the tasks. And after that, we also talk about the framework, training parameters, and input template, and also the evaluation for the current multimodal large language model instruction tuning framework. And then we also talk about the details about how can we generate the pre-training data, and also like the instruction tuning data for the multimodal large language model. And finally, we also discuss some like the challenge within multimodal large language model, like the hallucination, and also like how can we mitigate the hallucination problem. Oh, thank you so much. Here's the end of my talk. Do you have any questions?
Yeah, we will have a few minutes for several questions. Please. Okay, we got one question.
Okay, thank you. about the negative examples in the training dataset in order to
That's right.
To address, yes, the hallucination. What is the ratio of the negative example against the positive examples in the dataset that you found helpful? Thank you.
Yeah. Thank you for your question. Like, yeah. In the LRV instruction tuning dataset, the ratio of the positive and negative sample is 1:1. So because like in the experiment, they found like if the ratio of the positive sample and negative sample is same, is 1:1, the result will be better. So if maybe the positive sample or the ratio of the positive sample is larger than the negative sample, maybe the influence will be decreased a little bit. Yeah, if you have more questions, you can look into more details of our SLR paper, the mitigation hallucination in large multimodal robust instruction tuning. Yeah, thank you.
Okay, guess no more. Oh, please, one more.
Yeah, sure.
Okay. Thank you. Could you go back to the slide with this visual illusion with several circles? Yeah.
This one?
Yeah, the circles you just passed.
Oh, yes.
Yeah. So in fact, it's a very classical visual illusion. Of course, if you ask the normal people, in fact, to humans, to the question on the left, in fact, most of the people will answer no. The right orange circle is smaller than the left orange. It's just common sense. It's just a normal brain illusion. So, what is the truth? In fact, what you are seeking for? In this case, it's perhaps interesting to add to the prompt that you keep how to say the second answer is possible if you consider visual illusion. So that's a problem of common sense versus truth. What is your comment about this?
Oh yeah. Thank you for your question. Yeah. Your comment is very interesting. Yeah, because like I think even for human, for the first question, it's like a visual illusion. So for some guys, they may not answer it correctly. But there are some other examples within the hallucination bunch paper. Maybe like let me see, maybe like if the image like contains like two lines, and maybe we have two lines and the length may be different, and then we found like the model with the for GPT-4 it also may answer it incorrectly. And also we have some other examples, like maybe like for the map or maybe for the charts. So because if you are interested in the paper, in this kind of like example, you can look into the hallucination bunch paper, which contains many this kind of examples with many different categories. So you can have idea like how they perform, how like GPT-4 or maybe like a lot of perform on this kind of examples. Yeah, and so yeah, if that answers your question.
Okay, the question has been answered. Thank you. Okay, I guess we move on to the next presenter. Thank you, Fuxiao, for your wonderful presentation. Okay. So next we have Zhuosheng Zhang. And so Fuxiao, please transfer your host role to Zhuosheng.
So let me I mean I should open the security button, right? So and how can I?
You should do it in this panel.
Oh, what about I just quit, and will we transfer the host to Zhuosheng? If I just quit right now.